So once you've constructed your pellet, you want to load it into FTIR. You're going to use that attachment here and slide it into the device so that the thermo is up, and you can read that word thermo. And then that window that you made, you put it in there in the beam between the light source and the detector, and then you close the top. Now on the computer next to the instrument, you are going to open up the ohmic software and wait a little bit here. You see up top right now it says default, the default experiment, and you don't want that. It'll figure out that it's in transmission mode, and you saw it just automatically loaded the transmission experiment. That's important. You want to make sure you're running the right experiment. So it should say transmission, ESP up top. When that's all set, you're ready to collect your sample. You need to collect a background, but it's going to make you do that. So go ahead and enter a name for the spectrum. And when you collect this background, you want nothing in the instrument, or just the attachment. So it should just be shooting the beam through the air. And it's really taking an IR spectrum of the air. And those two big peaks in the middle there you're seeing around 2250 correspond to CO2. And you see at the bottom here it says 13 out of 32, now 16. It's going to collect 32 spectra, and you want to just let it finish, collect all 32 spectra. And every time you take a spectrum, it's going to force you to take a background before you take a spectrum. And for the background, you want to make sure that you have the sample out of the instrument and you're just shooting the beam through the air. Now you load in your sample, and after you've loaded your sample, you hit OK. Now I encourage you to run a blank as your first thing, so as your before you actually run anything. So don't put a sample in and just shoot it through the air again, and verify that you essentially see no signal. And this is good. The signal that you see now is essentially nothing. You see that the transmittance is at 100% throughout the whole spectrum, and that means all of the light is transmitting and there is no sample to absorb it. So when you run a blank, that just ensures, it gives you extra peace of mind that everything is running properly. And when it finishes all 32 scans, you have your blank spectrum. You can analyze it or you can look at it later, but really importantly, you want to save your work and save it in the CHE 433 folder, 433L folder, and within that folder, make a new folder with your name and save your work under there so that you can look at it later. So now we'll analyze a spectrum that I've already run. So this is something I already ran previously, and this is a pretty good looking spectrum. You can see that the background is up around 80% transmittance. It's well above 50%, and that's good. And the peaks themselves don't really go below 5%. And you want there to be a nice baseline at a high transmittance and then good peaks at a lower transmittance. Now that we have a good spectrum, one way to start analyzing it if you have no idea what it is to do a library search. So you want to make sure the library is set up first. So you go up here to Library Setup, and then in the library setup, you make sure that you have appropriate libraries selected. You really want the condensed phase sample library, the forensic chemistry, and then the Georgia Crime Lab sample lab. So once you have an appropriate library selected, then you can just click Search. And what this is going to do is compare your spectra to those spectra in the database. And you can see the top hit here is benzocaine, and it looks like it's a good match. However, it's really important to note we do not make identifications based on library searches. You can click on that top hit and click Overlay, and you can compare the spectra. But really what we're going to do is say, okay, we think it's benzocaine, so now we need to compare it to an actual benzocaine standard run under the same conditions. So what we mean by that is, even though this looks good, it looks like a good match, it's not your spectrum. It wasn't, you don't know if it was run under the exact same conditions. So we think it's benzocaine. So now you go get the benzocaine standard and you make a window of that and you analyze it under the exact same conditions that you analyzed your sample. And if those two spectra match when they're overlaid, then you can call it positive. So here's an example of two overlaid spectra. And what we've done here is we've taken our unknown, we've run it. The library search told us it looked like procaine. So we went and got procaine and then ran it. And now we're comparing the two spectra. And you can see the one in the blue is a very nice spectra. The one in the red is a little bit rough. There's a little bit too much sample in there. The starting background at around 4,000 is already down to 60 or so reciprocal centimeters. However, you see that these guys match up pretty nicely. Students often ask how to match up spectra, and it's really kind of pattern matching, but go through at each point and match up on the x-axis each peak. Does every peak match something? Even though here the magnitude's a little bit off, does each peak match something? And the answer is this case. This is a decent match, but if it were me, I would go back and rerun the red spectrum because the sample's a little bit too concentrated and it's distorted the spectrum a little bit.